Hi, I'm Ruomu. I will present our work on novel blockchain design called OHIE. This is a joint work with Hyphon, Ivica, and Pratik. We are from National University of Singapore. Blockchains have attracted huge amount of attention in recent years. They enable a network of nodes to agree on a pen-only distributed ledger. While these distributed ledgers have been commonly used to implement cryptocurrencies, they also have many other usage scenarios, such as in general finance, in logistics, and in healthcare. Early blockchains often have fairly low throughput. For example, Bitcoin has a throughput of 7 transactions per second. Modern blockchains have been able to achieve orders of magnitude higher throughput via various beautiful techniques, ranging from sharding to better consensus protocol. Despite Bitcoin's low throughput, the core of Bitcoin, Nakamoto consensus, still stands out in one critical aspect. It's remarkably simple. Nakamoto consensus can be fully described in a few dozens of lines of pseudocode. Simplicity always enables more reliable implementations, as well as easy reparametrization in different deployments. Perhaps more importantly, the simplicity of Nakamoto consensus has facilitated security proofs and cross-validations by multiple independent research groups. The importance of keeping constructions simple enough to allow such formal proofs and cross-validations cannot be overemphasized. Consensus protocols are notoriously difficult to analyze in the presence of Byzantine failures. Formal proofs are especially important to protocols that are difficult to upgrade once deployed, for example, in cryptocurrencies. Since simplicity is always good, we want to ask, is it possible to retain the simplicity of Nakamoto consensus and at the same time achieve much better throughput? We give a yes answer to the earlier question. By composing parallel instances of Nakamoto consensus, we propose a novel blockchain OHIE. OHIE uses as many instances as Nakamoto consensus as the network bandwidth permits, and its throughput scales linearly with the number of parallel instances. The simplicity and modularity of OHIE enables us to obtain a natural security proof that is based on reduction from existing analysis on Nakamoto consensus. Specifically, our reduction proves OHIE's safety and liveness under adversarial computation power fraction f for any constant f below 0.5. We have implemented a prototype of OHIE and have run experiments with up to 50,000 nodes using our prototype. Under similar settings as in previous works such as Algorand, our results suggest that while explicitly focusing on simplicity, OHIE retains the high throughput of modern blockchain designs. Specifically, our evaluation shows that OHIE throughput scales linearly with available bandwidth as shown in the figure. For example, under 20 megabit per second per node bandwidth, OHIE achieves about 10 megabit per second throughput. This translates to about 2,500 transactions per second, assuming 500 byte average transaction size as in Bitcoin. Such throughput is comparable or better than state-of-the-art permissionless blockchain under similar settings. Second, regardless of the throughput, the confirmation latency for blocks in OHIE is always below 10 minutes in our experiments, and the security parameters comparable to Bitcoin and Ethereum deployments. Finally, our experiments show that the decentralization factor of OHIE is at least an order of magnitude better than previous blockchains. In the remainder of this talk, I will first describe the problem statement and the security model, and then present more details on OHIE's design. Blockchain is a distributed system where nodes agree on a growing list of blocks. This list of blocks should be append only and should be replicated on every node. For those who are familiar with Bitcoin, this list is formed by the blocks that are at least 6 blocks deep in the longest chain. Formally, the system guarantees safety and liveness. Safety requires that the list order should be consistent among the nodes, and liveness requires that honest blocks are included in the list at a healthy rate. We know that while different applications of blockchain requires different properties, total ordering blocks will lead to many of the desirable properties in applications, such as no double spending. That's why we care about total ordering. For the security model, we use the same one as Nakamoto consensus. We consider the permissionless setting with proof of work. We assume that honest nodes form a well-connected synchronous overlay network so that an honest node can broadcast a block of fixed size within some amount of delay. For the security analysis, we follow the formal framework in CCS 18 and Eurocrypt 17. Now, let me talk about the details in OHIE's design. I will talk about the design in two parts. First, how are blocks mined? And second, how to produce a total order on the blocks. OHIE composes many parallel instances of Nakamoto consensus. To understand OHIE's design, let's start with an example of a single Nakamoto consensus instance. In this example, we choose to use a relative small block size of 20 KB. This small block size serves to keep the block propagation delay small without a significant overhead. Notice that the size is similar to Ethereum block size. Let's assume that the block propagation delay is around 2 seconds. The expected time in mining two successive blocks is chosen to be 10 seconds because when the interblock time is at least 5 times of the block propagation delay, existing formal results have shown that Nakamoto consensus has nice safety and liveness properties as long as f is below 0.43. Do know that under these parameters, Nakamoto consensus has fairly low throughput since it only generates one 20 KB block every 10 seconds. Next, assume that the system could compute 2 to the power of 60 hashes in 10 seconds. Then, each valid block should have 60 leading zeros in its hash value. Now let's see how OHIE can use 1024 such Nakamoto consensus instances in parallel. Previously in Nakamoto consensus, we require each block hash to have 60 leading zeros. Now in OHIE, with 1024 parallel chains, we only need each valid block to have 50 leading zeros. Another 10 bits of the block hash is used to assign the block to one of the 1024 chains. Note that our system is not a sharding scheme, as every single node is working on all 1024 chains at the same time. It's critical to notice that for every given chain in OHIE, the probability of a single hash generating a valid block for that chain is still 2 to the power of -60. This is exactly the same when we had only a single Nakamoto consensus instance. In particular, the adversary cannot concentrate its hash power to a single instance. This in turn suggests that the probabilistic behavior of any given chain in OHIE, even when under attack, is the same as when we had only a single Nakamoto consensus instance. Our paper has actually formalized such intuition as a formal reduction. This ultimately enabled us to do a security proof based on reduction to the security of Nakamoto consensus. Now with all these 1024 chains, OHIE is generating 1024 blocks every 10 seconds on expectation. This means that we have improved the throughput by about 1,000 times. We used about 1,000 chains on the previous slides. What prevents us from using 1,000,000 chains? Well, this is restricted by the available network bandwidth. Note that we have been assuming that each block can be propagated to other nodes in about 2 seconds. As we use more and more instances, and as the network bandwidth starts to get saturated, the block propagation delay will increase. Hence, we want to use as many instances as possible without substantially increase the block propagation delay. Look at the figure there. Our real-world experiments show that we can effectively utilize up to about half of the raw available bandwidth without seeing a much increased delay. In Nakamoto consensus, when mining a new block, the miner will include the hash of the previous block as its parent. This serves to force the miner to commit to the block from which the new block extends. In OHIE, with all the parallel instances, the miner would not know to which instance a block belongs to until the block is mined and assigned according to its hash. To still force the miner to commit, we build a Merkle tree whose leaves are all the 1024 last blocks on the 1024 chains. The Merkle root need to be included in the new block. Conceptually, this forces the miner to commit to all the 1024 blocks. and the new block will eventually extend from one of them based on the hash of the block. We have shown how blocks in OHIE are mined. Now let's move on to how to order these blocks. Let's start with a single instance of Nakamoto consensus in OHIE. We follow the same way as Nakamoto consensus in ordering the blocks on a single instance. Specifically, the list is obtained by removing the last k blocks from the longest chain, where k is a security parameter. Let's define all the remaining blocks in the list as partially confirmed blocks. We have partially confirmed blocks on each single instance, and now we are to include the partially confirmed blocks into a single list. Let's look at a simple baseline design to generate the list. The baseline design orders the partially confirmed blocks by running over the chain one by one and put the smallest index partially confirmed blocks into the list each time. This ordering will take the first block on the instance 0 as the number 1 block and the first block on instance 1 as the number 2 block, and etc. Such process stops once it reaches an instance that runs out of partially confirmed blocks. All the blocks that have been included in the total order are defined to be fully confirmed blocks. The problem with this approach is that the probabilistic effect of mining may cause different instances to grow at different speed, even though the expected growth rate is the same. This means that a partially confirmed block on a fast-growing chain will have to wait for the slowest chain to catch up before it can become fully confirmed. In fact, our simulation experiments show that the possible size divergence across the chains can grow unbounded over time. When this happens, blocks on the fast-growing chains may have unbounded confirmation latency. Our idea to solve the long confirmation delay caused by different chain length is to assign each block a virtual size. We let the block on the shorter chains have larger virtual sizes so that all the chains will have roughly the same virtual length. Then, we apply the simple round-robin ordering while taking into account the virtual sizes. For example, in our figure here, if we give block 5 a virtual size of 5, chain 1 will have a larger virtual size than its physical size. Now, if we do round-robin ordering, we can immediately order block 8 after 7 and block 9 after block 8 and so on. This effectively makes all the partially confirmed blocks fully confirmed. We have shown that with seeing all these blocks, assigning virtual sizes helps to solve the length divergence problem. Now, how do we assign virtual sizes in a distributed way without having the global knowledge? Let me run through an example to illustrate the idea. Let's assume that one block is already mined on instance 1 and other instances only have a genesis block. With seeing these blocks, the miner first commits to all the latest blocks on each chain by including the Merkle tree roots in the block. Next, the miner needs to find a valid nonce for the block. As discussed before, a valid nonce should have 50 leading zeros. Once the nonce is found, based on other 10 bits in the block hash, the block is assigned to extend one of the instances. In the last step, the miner assigns the block with a virtual size. Let the total virtual size of the blocks on the longest chain be defined as the virtual length of an instance. Since instance 1 has the longest virtual length, the newly added block to instance 1 should have a minimal virtual size of 1. Let's mine another block to illustrate the case where the virtual size is larger than 1. Let me skip the first 3 steps in mining a block and focus only on assigning the virtual size. Suppose a block is mined on instance 2. In the miner's view, the highest virtual length is 3, and instance 2 has a virtual length of 1, and hence the newly mined block should be assigned with a virtual size of 3 minus 1 equal to 2 to make up for the difference. After the newly mined block is broadcast, we see now instance 1 and 2 have the same virtual length. With this way of mining blocks, let's assume more blocks are mined on instance 1 and 2. Now, because instance 0 is slow, many partially confirmed blocks cannot be fully confirmed. We then show that with just 3 new blocks mined on chain 0, OHIE will fully confirm all these blocks. The first mined block on chain 0 will have a virtual size of 7, helping the virtual length of chain 0 to match the highest value. The other 2 newly mined blocks will make all these blocks before length 8 partially confirmed. Now, with the round-robin ordering, all the partially confirmed blocks are fully confirmed. As shown in the previous slide, the virtual size is determined by the miner. Hence, the adversary may choose a bad virtual size when it mines a block, but this is not a problem. When the adversary chooses too small a virtual size, the only problem is that it does not help the slow instances to catch up. But this will not cause a problem because when honest blocks are added to the chain later, they will help the slow instances to grow. The adversary may choose too large a virtual size, but we can easily prevent this behavior by requiring a hash pointer to the existing blocks as a proof for the virtual size. I hope my presentation of OHIE has demonstrated the simplicity of its design. OHIE simply runs many parallel instances of Nakamoto consensus and then uses a simple trick to totally order the blocks across different chains. Such simplicity enables us to obtain a moderate security proof based on reduction from Nakamoto consensus. Earlier, I have also shown OHIE's excellent throughput, which is comparable to state-of-the-art high-throughput blockchains. More details are in our paper, and thank you very much for watching.